Hi, here we discuss about a project, a counter-based addition circuit designed for stochastic computing. Here, the convolutional neural network has become one of the most widely used adopted deep learning technique for image processing, object detection, medical imaging, autonomous systems, and intelligent edge devices. However, the conventional CNN hardware implementation required a multiple binary multiplier, wide adders, and divider circuit to perform a convolution and mean operation, resulting in high logic utilization, increased power consumption, and longer critical paths. For example, an 8-bit 3x3 convolution required a 9 multipliers that generate a 16-bit product, followed by a large multi-input additions and division circuit, significantly increasing hardware complexity. The stochastic computing provides an alternative, attractive method by replacing a complex arithmetic unit with a simple logic circuit, thereby reducing hardware cost and improved fault tolerance. In this work, the n-bit input counter-based addition circuit, which means a CBAC architectures, is employed as an efficient hardware building block for CNN convolution operation. The proposed implementation demonstrates support for both 2x2 and 3x3 CNN kernel using a same scalable CBAC architecture, and it's eliminating the need for conventional binary adders and divider circuit during a mean value computation. This architecture is designed in Verilog HDLs and synthesized on Xilinx Vertex 5 FPGA to evaluate hardware resource utilization, logic performance, operation cycles, and propagation delay and power consumption. The experimental results shows that the proposed CBAC based CNN architecture significantly reduced hardware complexity while maintaining efficient timing, performance, and low power consumption. The architecture provides a compact and scalable solution for stochastic CNN oscillator, making it suitable for low power, high performance edge intelligence application. Now we can verify the paper. So this paper is fully designed for the counter based addition circuit. Okay, the counter based addition circuit, here they calculating the bit of the vector. Okay, so the timing based measurement, it will be calculated with support of the counting. Okay, so here the figure 2 and figure 3 architectures, you can verify it. The operations of figure 2, the proposed CBAC, and the B is a digital pattern of the 3-bit counter. Okay, so it will be showing how this circuit it will be work. Okay, so here initially they start with the counter circuit. Okay, so this counter circuit will give a input to the x1 and x2 comparator. Okay, so this x1 and x2 comparator will compare the value of x1 input and x2 input, and it's analyzing the maximum value. Okay, so how much it will be suitable. Okay, so the x1 it will be close first, or x2 it will be close first. Okay, so it will be analyzing it. At the same time, it counting the AND gate of D1 input. Okay, so A1 it will be support with the D1, and A2 it will be support with invert of D1. Okay, after that it will OR the value and it will be given the pulses to the counter. Okay, so here this is a AAO unit, and OR unit. Okay, it will be used for the proposed novelty architecture. Okay, so here you can verify the digital pattern of 3-bit counter. So clock 1, 2, 3, 4, 5, 6, 7 clock it will be required. Okay, so D3 and D3 bar, D2, D2 bar, D1, D1 bar, it will be used. Okay, so for the supporting architecture, and this counter it will be initiated. Okay, so here it will be compared 2 by 5. Okay, 2 divided by 8 and 5 divided by 8, the output it will be present with this form. Okay, so if it is equal, okay, so it will be generated as 0 values only, otherwise it will be provided a 1 value only. Okay, so the next circuit of n-bit CBAC with the m-bit RNS architectures, it will be given and detailed with a 4-bit input. Okay, and additionally the example circuit for our analysis. Okay, so here you can verify it. The x1 is 9, x2 is 5, and x3 is 10, and x4 is 12. Okay, the output come with a 9 divided by 16. Okay, so here the numerator and the denominator it will be used for this mean value. Here denominator it will be same for input and output side, but the numerator only calculated for the mean value. Okay, so here example, we can use a calculator and we calculate it. Okay, so here 9 plus 5 plus 10 plus 12, so this is a numerator value from x1 to x4. Okay, totally 36 divided by 4. Okay, the output is 9. Okay, so that's why the output come with a 9 divided by 16 in the output side. Okay, so here the input, it will be compared with a d1, d2, d3, d4. Okay, and then it will be calculated with the supporting architecture of AAO method, and then it will produce the final output. Okay, so here this one is a only AAO and another AAO, and this is a another AAO. Totally 3 AAO architectures they will be used to find out the original value. So for the supporting, we used D1 and D2 architectures for calculating the comparisons. Okay, so here the D1 is used for the first 2 AAO and D2 it will be used for the second AAO. Okay, so the same method it will be copied here, the n bit size. Okay, so this is a 4 input architecture. 4 input architectures means it's come with a 2 cross 2. So in CNN 2 cross 2 means it will be come with a 4 pixel value. The 4 pixel mean value we can take an easily. Okay, so if we change this architecture to 9, okay, it will be support for 3 cross 3 CNN. Okay, so 3 cross 3 CNN architectures also mean value we can take an easily. Okay, so that it will be used for image processing architectures in this paper. Okay, so here they already done some image processing work. The 3 cross 3 approximate Gaussian smoothing window they will be designed. Okay, but in our work we design only the counter part of the mean value. Okay, for 2 cross 2 and 3 cross 3 only we have analyzers for this project. Okay, so if additional novelty required or additional thing required, we can elaborate this work and we can use it on multiple applications. Okay, so first of all we need to prove these architectures in a good comparisons. Okay, so here the 2 cross 2 and 3 cross 3 architectures we have designed in Verilog HDL and synthesized on Xilinx Vertex FPGA. Okay, this is a Verilog HDL code for 2 cross 2 and so this is a Verilog HDL code for 3 cross 3. And this is a simulation report. Okay, so here x1, x2, x3, x4. Okay, so here the data check value we generated, and here output you can generate it here 7 7 5 5 11 11 6 6 3 2 3. Okay, and you can check anywhere. Okay, so some of the cases it will be produced approximate output. Okay, all the outputs not inaccurate. Okay, so first understand that one. Okay, so here you can check this value 14 plus 12 plus 1 plus 11 divided by 4 equal to 9.5. Our data check output is 9 and generated output is generated output is 8. Okay, so as per this shifting process here the data it will be match approximately equal. Okay, so here the real output is 9.5 and it will be showing 9 and output come with the 8. Okay, so here if you are check with this circuit 12 plus 12. Okay, 12 plus 12 plus 7 plus 1 divided by 4, the output come with a 8, but the output come with here 9. Okay, so most of the cases it will be equal in a data check value, but it will take some delay point. Okay, so here you can verify the waveforms. Okay, so it takes some delay in result count, but it's mostly come with the same pattern following in the input and output side. Okay, so here this circuit we validated with the verification side. Okay, okay, and the next architecture is 3 cross 3. Okay, so here this is the simulation results. Okay, so here you can analyze it, the result count value and data check value. Okay, You can analyze this. 120 is a generated input and 122 present, 94, 96, 97, 98, 147, 147, 142, 144, 116, 117. Okay, so here this is a 8 input architecture. Okay, so from the 3x3 image processing architectures, okay, so all the 8 pixels will be taken a mean value, and the main output will be placed it on a center of the pixels. It will be support for the application of image denoising, pre-processing for computer vision, medical image processing, satellite, remote sensing, and documentation, image processing, video processing. Okay, so all the processes will be support the 3x3 mean filter. Okay, so to take the 9th pixel value. Okay, so this work we have synthesized in Xilinx Vertex 5 FPGA. Okay, so here the CBAC architectures. Here this is a 4 input counter based architecture. Okay, and this is a logic size, and this one is a 8 input architecture. Okay, so here you can verify the RTL schematic. Okay, so here we have used number of comparators and AAO array architecture and counter and result counter architecture. Okay, so in this AAO architectures we have used AAO1, AAO2 and AAO unit. Okay, so AAO1 will be present with the number of AAO unit, and AAO2 secondary, and AAO3 is the final one. Okay, and this all parameters comparisons we updated in the document. This is a comparisons, and we have created abstract document for this project. Title, base paper, improvement and proposed title, proposed abstract, advantages, disadvantages, proposed system, and related notes for this project. Okay, literature survey and references. Thank you.
Are you planning to publish your next innovative research in IEEE Transactions on VLSI 2025? Welcome to NXFE Innovation, where future-ready VLSI research projects are designed with novelty and quality for global researchers. At NXFE, we provide novelty-based VLSI projects carefully aligned with IEEE Transactions on VLSI 2025. These projects are not yet published, offering you a clear opportunity for unique contributions in top-tier journals. Our research covers key domains like low-power VLSI design, analog integrated circuits, FPGA implementation, signal processing architectures, and emerging applications such as cryogenic front-end ASICs, physical unclonable functions, and self-recycling SRAM cells. Each project comes with a verified novelty, simulation results, and complete customization for your journal publication. You'll find practical design files, HDL codes, schematics, and step-by-step explanations to guide your research journey. We provide 100% accurate results and comparisons of source code with all results, basic documentation, and explanation video. We provide execution support with explanation recorded video explanations on your system. IEEE guidance for paper writing and journal publication. Affordable project packages with ongoing support. Customization to match your research needs. Early bird offers and discounts for researchers. Don't miss the chance to publish in IEEE Transactions on VLSI 2025. Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research.